This video we're going to be talking about differentiating trigonometric functions. Now we've already covered things like differentiating polynomial functions. We've covered the chain rule, the quotient rule, the product rule. So now we're going to talk about trigonometric functions and then apply all those rules, the chain rule, quotient rule, product rule, to doing trig functions. This first page here just goes through the proof of the basic derivative of sine x. So this is the formal proof using differentiation from first principles. So this formula here for the derivative is like the most basic formula that we can have for what the derivative actually means. You don't need to know how to do this proof. So it's in there. I'm not going to go through it. You can have a look at it. But the upshot of it is that the derivative of sine of x is cos of x. Let me just look at that graphically because I think it's a good way to appreciate this. So the red line here represents y equals sine of x. So let's look at the slope at each point. So if we start off there, if we look at the tangent or the slope of the tangent there, you can see it's pretty close. When sine of x is 0, you can see that it's pretty close to 1. When we get across to here, pi over 2, the slope is 0. And you can see that as we move across the sine curve, the slopes are decreasing there. Okay, so they're getting smaller and smaller. When we get to this point right here, if we drew a tangent to the sine curve, it's round about -1. Okay, so if I drew down here, it's about -1. You can quickly see that I'll build up a picture where the derivative, the slope of the red curve at any place is just this blue curve here. Okay, and we know that that blue curve there is y equals sine x. Y equals cos x, I beg your pardon. So the derivative of sine of x is cos of x. Now if we were to do the same thing for cos of x, let's do that, and I'll do the same kind of graphical approach. So if we started with the blue curve and we wanted to know what's the derivative, well, we could see it's 0 right here. So the slope of the blue curve is 0 there. I can see the slope of the blue curve at pi over 2 is -1. I can see the slope of the blue curve here is 0. So I'm just in the red marks here, I'm just marking off what the slope is. I can see the slope here is 1 and the slope up here again is 0. So if I build all those up, just taking away those gradients, if I build all those points up and kind of join them, I get something that looks like this. Okay, that to me looks like the graph of y equals negative sine x. So it's the graph of sine of x, but instead of going up, we go down. It's just negative sine of x. So two important results then. D by dx, that just says the derivative of sine of x is cos of x. And secondly, the derivative of cos x is negative sine of x. Okay. You can see, let's do some work with the chain rule now. So if we've got y equals sine 3x, we know the derivative of sine of any function is just going to be cos of that function, but we also have to take into consideration the 3x here and the derivative of that. So this is the chain rule coming in. Because the derivative of 3x is 3, we end up with an answer of 3 cos 3x. Okay. Sine of 2/3 x, the derivative of sine 2/3 x is cos 2/3 x times by 2/3 because of the chain rule again. This one here is a little bit trickier. Sine squared x is the same as sine of x squared. So if we use the chain rule, we bring that number down the front, subtract 1 from the power, multiply by the derivative of what's inside the bracket. So we get 2 sine x to the power of 1, and the derivative of sine x is cos x. So we get 2 sine x cos x, which some of you may recognise as sine of 2x. So a typical question that we might have done last year might have been 2x minus 1 to the power of 5. If we have that, the chain rule told us that the derivative looks like this. Number down the front, subtract 1 from the power, multiply by the derivative of what is inside the bracket here. So 10 2x minus 1 to the power of 4. So I'm just applying that same rule here. Okay, I'm going to zoom back up a bit, a few pages, and do some more examples here. You'll notice that there's also a proof up here for how to work out that the derivative of cos x is negative sin x from first principles. Again, you don't have to know how to do this, but it's there in case you want to know how to do it. And there's the one for sin of x. Okay, let's just do some more examples, and I want you to fill these examples in. So for this one here, the derivative of x squared minus x cubed. I'm just going to write down the derivatives. So that's just going to be 2x minus 3x squared. We know those derivatives rule for polynomials. For b, x squared plus sin x, the derivative would be 2x plus cos x. So if you have a sum of two terms, you just do the derivative of each individual term. Second example, the product rule. We don't really need the product rule for a. We know the derivative of 3x squared is just going to be 6x. And for 5 sin x, the derivative is just going to be 5 cos x. So we can just leave the 5 out the front, forget about it, do the derivative of sin x, then bring the 5 back in. Now we need the product rule more for this one. So 3x minus 4, I'm going to say that u is 3x minus 4. And v is 5x squared plus 3. U dash is 3, v dash is 10x. Product rule tells us that the derivative is u dash v plus v dash u. That's the formula from last year. So u dash times v plus v dash times u, which is 3x minus 4. So if you carefully set it up like that, you won't go wrong. You'll get these right. For this one here, we can expand out the brackets and simplify. So 15x squared plus 9 plus 30x squared minus 40x. So we've got 45x squared minus 40x plus 9. Okay, but you got the basic idea there of how to use the product rule. So I can apply that now to part B of this question, which said 2 minus cos x and 1 plus sin x. So I'm going to say u 2 minus cos x, v is 1 plus sin x. Okay, u dash. The derivative of cos x is negative sin x. So the derivative of negative cos x is just sin x. So the derivative of cos x is negative sin x. So the derivative of negative cos x will just be sin x. Okay, so the derivative of this one here is sin x. That took a bit of getting to. And the derivative of this one here is easy. 1 plus sin x is just going to be cos x. Okay, so altogether, the derivative is u dash v plus v dash u. Here we go. Now we can leave it like that, but there is some simplifying to do here. Sin x plus sin squared x plus 2 cos x minus cos squared x. Now in this case here, nothing simplifies here. We could use some trig identities for sin squared minus cos. There is some stuff that we could do there, but I'm happy to leave it just like that. Just demonstrating how the product rule works. Okay, so that's the product rule with some trig examples. Quotient rule. First of all, a reminder how to do the quotient rule. Okay, so here we've got u is x squared minus 1, v 2x minus 3, u dash 2x, v dash 2. The quotient rule says the derivative is u dash v minus v dash u over v squared. So that's the formula for the quotient rule. So when we've got two functions divided by each other, we can't simplify it anymore. So I'm just going to put everything in. U dash v minus v dash u divided by v squared. Now you can leave it like that, but I really like to tidy the top up. So on the top line here we've got 4x squared minus 4x squared there, minus 2x squared. So that's going to give us two lots of x squared. Then we've got minus 6x, that second term there, and then plus 2. 2x minus 3 squared. That may help us if you do that. Recall, it may help us if we're trying to solve when is this derivative equal to 0. We know that's when the top line there is equal to 0. So it may help us if we simplify that to get an expression that we know that we can then solve equal to 0. Which I'm not sure if this one here works. Okay, so second part, using the trig stuff. We've got sine of x over cos x. This is a pretty easy one. So u is sine of x, v is cos of x, u dash cos x, v dash negative sine x. Okay, let's put this all together. So the derivative is going to be u dash v minus v dash times u divided by all of that stuff there divided by v squared. So that's just going to be cos squared x. Cool. So on the top line you can see that we get cos squared x minus minus gives us a plus sine squared x over cos squared x. And we know the identity that the top line there is just 1. So that's 1 over cos squared x, which we know that better as sec squared x. So the derivative of tan of x, which is sine over cos, we just use the quotient rule to show that that is sec squared x. Okay. So that's from that result right there, and that's how we get it using the quotient rule. The chain rule is probably the one that's the most common that you have to use with these trig derivatives. So I'm going to skip straight to b here. We've got y is equal to sine of 2x plus 1. Let me do this the long way. And we're going to say u is 2x plus 1. So that means that du dx, the derivative of u with respect to x, is 2. So our original function becomes y equals sine of u. Cool. So we can say now dy du, the derivative of this function y with respect to u, is cos of u. Okay, now let's put it all together. What we want is dy dx. And the chain rule says that is dy du times du dx. Okay, you can see how this would work. Those two could cancel there and we're left with dy dx. So that's how the chain rule works here, behave with these derivatives behaving like fractions. Because they're not actually fractions, but they behave like them. So dy du is cos of u, and du dx was 2. So I can just write that as 2 times cos of u, and we know u is 2x plus 1. Done. So there's the derivative in terms of x. The shorthand here is just, like I said, for sine of 2x plus 1, the derivative of sine of a function of x is cos of that function of x times the derivative inside it. So let me write a conclusion for that in red. If you have y equals sine of some kind of function of x, the derivative is cos of that function of x times by f dash x. Okay, I'll just put brackets around that as well. So that's the formula that I'm using here for the chain rule for these trig functions, and the same thing applies for cos. So if we have y equals sine to the 4x, which is the same as sine x to the power of 4, then the derivative is going to be 4 sine of x cubed times the derivative of sine x, which is cos x. So I can write that as 4 sine cubed x cos x. So there's another one done using the chain rule. Let's do this one, tan cubed x. Okay, so the derivative is going to be, tan cubed x is tan of x cubed, so 3 tan of x squared. So we're just leaving that tan x like a function inside there. Number down the front, subtract 1 from the power, and we know we just learnt that the derivative of tan of x was sec squared x. So I've got 3 tan squared x times sec squared x. Now you could leave it like that, I think that would be fine. If you do want to simplify it, you could do something like this. That's sine squared over cos squared x. Sec squared is 1 over cos squared x. So sometimes, you know, things will simplify. Here it doesn't. So I could write this as 3 sine squared x over cos to the 4x. But that's no simpler than what we had originally. So there's the answer for the derivative of tan cubed x. Okay, this is the challenge question for this video. Bit of an application of trigonometric derivatives. Here we've got a rugby field. We've got the posts that are 6 metres apart. The right-hand post here is 19 metres from the corner flag. This is a kind of a calculus applications question. And now what I want to do is, if a try is scored right here in the corner, I want to know how far back should the kicker take the ball so that the angle that he sees between the posts from where he's standing is as big as possible. That's what this calculus is all about. It's about maximising, minimising rates of change. So this one here, we want to maximise the value of theta here. And we want to know what value of x maximises that value of theta. I've got some clues here. First thing to note, that if you maximise the value of tan theta, you're maximising the value of theta, because that graph there is just going up. So the bigger value of tan theta you get, that's going to give us a bigger angle for theta. And I've also given you a formula here we did last year for tan of A plus B, or tan of A minus B. That will be helpful as well. Let's see if we can answer that question.